In the final part of this lecture, we will study the quicksort algorithm. So what is quicksort? So quicksort is an algorithm for sorting numbers. We want to use this algorithm to arrange an input set of numbers from small to large. Now the main idea here is very simple. So we first randomly select a certain number from this set of numbers to be sorted. And this number, let's call it x, is going to be compared with every other number. So we will call this x the pivot, just like the pivot when you play the seesaw. And using x, by comparing x with every other numbers in the set, then we will divide the numbers into two groups. One that is smaller than x, and the other group are all the numbers greater than x. Now, because of this, then after the second step that we are describing here, then we will know that what is the correct position of x in the sorted numbers. So after that, what we remain to do is we'll find a way to make those numbers smaller than x to sort, and then those numbers larger than x to be sorted. So we are going to apply the same idea recursively on the smaller numbers and also on the larger numbers. So this is quicksort. So a quick capture of this algorithm is like this. Okay, so quicksort is a recursive algorithm by the sense that we are going to apply quicksort inside itself. The boundary case is when you don't have any numbers to sort, or when you have just one single number, we will return the number directly. Otherwise, the set S will contain more than one number, so we can select a number x from it, use x to divide the numbers into two sets, S1 and S2. S1 are the smaller numbers, and then S2 are the larger numbers. And after that, we perform quicksort on S1 to get a list of numbers sorted. We perform quicksort on S2, we get another list, which are the numbers that are larger than x to be sorted. And finally, when we return first of all the list 1, and then x, and then list 2. So this should be the case where all the numbers are sorted. Now the correctness of quicksort can be proven by using induction, so I'm going to skip this. Now, let us take a look at the performance. So suppose that there are n numbers to be sorted. Then in the worst case, we will see that every two numbers could be compared with each other. Now this scenario may happen in the following case. So suppose that in the first step, x that we are choosing turns out to be the smallest number of the whole set. Then x will be compared with everyone, but then finally we will put all the numbers into the larger group. And similarly, when we are trying to solve the problem recursively, then we are selecting the smallest number of this set again, which is going to be compared with every other number, and so on and so forth. So in such a case, then we are going to create a lot of comparisons. So in the worst case, the number of comparisons will be equal to n times n minus 1 over 2 in such a case. Now notice that two numbers can only be compared at most once. The reason is that when we compare two numbers, one of them must be a pivot. And in such a case, the pivot will never be compared with another number with the same number again in the future. Now quicksort could have, this is like a worst case, which is very bad. It is like n squared. And there are actually faster algorithms in theory, but in practice, there are still many people using quicksort. And what is the reason? Okay, the reason is that it is very unlikely to hit the worst case that I've just mentioned. Now, the good point about quicksort here is that when we select a certain number as the pivot will separate the numbers into two groups. And then, after this separation, any number from the first group will never be compared with any number from the second group. So in such a case, then we are going to enjoy the process of, like, we try to compare each number theoretically so that we know which one is larger, which one is smaller. But by using the pivot, then we save a lot of comparisons. And so, because Quicksort have some randomization applied inside, because we are randomly selecting a certain number as the pivot in each step, so we may wonder, what is the expected number of comparisons needed in this algorithm? So let's say there are n numbers to be sorted, and then without loss of generality, we may just relabel the numbers as 1, 2, 3 up to n for simplicity. Now, so the numbers to be sorted are exactly this 1, 2, 3 up to n, okay? And then we define a random variable xij to be the number of times that this I and j within this set of numbers, they are compared. So the expected number of comparisons is simply equal to, by using linearity of expectation, it is the summation of expected value of xij for all possible pairs of ij. So here we restrict I is less than j, because we are not, so I is compared to j is meaning the same as j is compared to I, so we restrict I to be less than j. Now, so we have some key observations here. So the first one we have already mentioned. Any two numbers can only be compared at most once, because it is compared when one of them is the pivot. And xij is equal to 1. So the number I and j are actually compared. We will see that it happens if and only if among the numbers between I to j inclusively, so I plus 1 up to j, I or j are selected as the pivot earlier than any of the numbers here inside selected as a pivot. Because if any number in between, strictly in between, are selected as a pivot, I and j will have no chance to be compared. On the other hand, if I is selected first, I will compare with everyone here, so I will be compared with j. And similarly, when j is compared is selected as a pivot first, j will be compared with I. Now remember that our algorithm chooses pivot randomly. So we can really find out what is the chance that I or j will be selected first among all the numbers from this group. So this is what we have. So expected of xij, it is an indicator. Xij is an indicator, so it is equal to the probability xij is equal to 1. The chance that xij is equal to 1, that is xij, that is I and j are compared, is exactly 2 divided by, there are so many numbers, j minus I plus 1 in the collection. Okay, so this is easy, right? Now we have everything. So from before, we have expected number of comparisons is the summation of xij, and now we have the exact formula for xij. So we can combine everything so that we get the corollary here. So the expected number of comparisons in Quicksort is order of n of n. We are going to show this one. So although that the worst case is n squared, order of n squared, but the expected number of comparisons is only order of n. So we combine everything. So summation of I less than j, E of xij is the expected total number of comparisons. So to be more specific, we are ranging I from 1 up to n minus 1, and then ranging j starting from I plus 1 up to n. And then we are going to find out what is the expected value of xij. Okay, so we now replace xij by the formula that we have just computed, which is 2 over j minus I plus 1. Now notice that this term sums everything from I plus 1 to n. So it will be smaller than or equal to if we sum everything from 1 up to n. If we sum everything from 1 up to n, then this term is simply 2 times h of n. So we established that the middle equation here is strictly, okay, maybe not strictly, it depends on n, okay, is smaller than or equal to if we replace this summation part as 2 times h of n. And then there are at most n terms here, there are n minus 1 terms here actually. So if we talk about the order, h of n has order log n, and there are n terms of 2 times h of n, so there is going to be order of n times log of n. So this explains why people may choose quicksort, because quicksort is easy to understand, easy to implement, and also it has a very good expected performance. But actually more than that, okay, we can later, okay, so if you check the textbook, okay, there will be an exercise in chapter 4, exercise 4.20. So in this exercise, we are going to show that this quicksort method actually uses order of n log n comparisons with high probability. So in most of the cases, then it is really order of n log n. So this is the true reason why people are still using quicksort, despite the worst case could be n squared. Now another thing to talk about here is that in the implementation of this randomized quicksort, we are selecting a random pivot in each step. But there is another way to do so. Okay, we may replace this random selection by first shuffling the whole input from only one time at the start, so that all the items in the input are now in random positions. Then for each recursion, we will pick the first number in the list as the pivot. So in that case, each number actually that is remaining in the recursive step, we have equal chance to be selected as the first number. So that is meaning that we are selecting any number with equal chance to be the pivot. So that's the end for the discussion of quicksort.